So the last talk of the session will be given by Nils, I think.
Yeah, it's remote, sorry.
And it's remote.
Okay, so I assume you can hear me. So I'm Naïm, and this is joint work with Nils Danielsson and Ondřej Kubánek on normalization for first-class universe levels. So our sort of running example is going to be the polymorphic identity function, which is something.
Wait a second, we don't have your slides yet in the room.
That you can define in any language that has some sort of parametric polymorphism. So in dependent type theory, the way that we express that is using universes.
Hello, can you hear us?
Yes, hello?
You're not sharing your slides.
Oh, I'm sorry.
It's okay.
Okay, here you go.
They're in continuous mode. Okay, yeah, got it.
I can barely hear you.
We can see them.
Okay, good. So in dependent type theory, we use universes for many different reasons, but so polymorphism is one of them. So a universe is just a type of types. And if we have dependent function types, we can just say that the identity function takes an element of the universe, so a type, and returns a function from A to A. But universes have a sort of well-known limitation, which is that we can't have a universe of all types because that's inconsistent for the same reason that we can't have a set of all sets in set theory by Russell's paradox. So this means that we can't use this identity function for the universe itself. So we can't apply it to a type, which is not so nice. So the usual solution to this is to stratify the universe into levels. So for example, if we start with a base universe U0 of small types, we can add a larger universe U1 that contains U0, and we can actually keep going. So if we want every type in the theory to be in some universe, then we can just keep going up to infinity. So in this case, the universe levels are just the natural numbers. You can have other hierarchies. There's a really cool paper by Favier, Carlo Angiuli, and Reid Molenix on an order theoretic analysis of universe polymorphism, where they show that universe hierarchies don't even have to be well-founded. You can have the integers, or the rational numbers, or crazier things. But I'm not going to talk about that. So stratification leads to another problem, which is that we now have duplicated definitions across universe levels. So, on paper, we could just write the definition once and let the reader understand what we mean. But if we're designing a proof assistant, we really need some kind of mechanism to avoid duplication. So there are a couple mechanisms for this. One of them is to just pretend that there's only one universe and let the type checker or the elaborator guess what we mean. Another solution is universe polymorphism. So this is basically to universe levels as polymorphism is to types. So in a system with universe polymorphism, we could write the identity function like this by quantifying over levels. And I think most existing proof assistants have something like this in some shape or form. The proof assistant that I care about is Agda. So Agda goes one step further and internalizes the levels as first-class objects. So this is sort of the same move as going from polymorphism to universes, where we sort of internalized the collection of types as a type. Here we are internalizing the collection of levels as a type. And so this is finally how we write the identity function in Agda. So we use two dependent function types, one over levels and one over types. And so having first-class levels gives us a lot of extra power. So aside from getting universe polymorphism, we also have the ability to quantify over levels in a sort of nested manner. So we get higher rank quantification. We can have levels that depend on elements of other types. So, you can define a function from the natural numbers to levels by recursion. In a similar spirit, you can put levels in arbitrary data structures. So this is actually used in the Agda standard library. There's a paper by Guillaume Allais that shows how to construct n-ary function types that take a heterogeneous list of types as the domain. And so since the types live in different universes, you also take a list of levels as an input to that construction. So one reasonable question to ask is, well, is this okay? And a more technical version of that question is, what are the meta-theoretical implications of first-class levels? So to make this even more precise, there are sort of three big semantic properties of type theory that we care about from three different sort of perspectives. So one of them is consistency, that I've already mentioned. So this makes sense from the perspective of logic. If you want to think of type theory as some kind of logical system for proving mathematical theorems, then you would like to know that there is no proof of a contradiction. In type theory, the way we say this is that there are no closed terms of the empty type. And this was proved by Ondřej Kovač in a paper on generalized universe hierarchies and first-class universe levels. So he constructed an inductive recursive model of type theory with first-class levels. So if you sort of believe in induction recursion, then you also believe in first-class levels, sort of. Another question is canonicity. So this is something that makes sense from the point of view of computation. So thinking of type theory as some kind of programming language, we want to be able to evaluate terms. So what this means is we would like closed terms of type natural number, for example, to be actually canonical natural numbers, as in concrete number literals. So this is a sort of characterization of the closed term of type natural number in the same sense that consistency characterizes the closed terms of the empty type. And this was also proved by Jonathan Chan and Stephanie Weirich in a recent paper about bounded level polymorphism, which is a bit more general than what I'm going to talk about. And so the remaining question is normalization. So this is a property that's important from the point of view of implementation. So if you're writing a proof assistant, you would like to know that it's possible to write a proof assistant in the sense that the type theory that you're trying to implement has decidable type checking. And the way that this is usually implemented for dependent type theory is using something like normalization by evaluation. So this is, these are all sort of related properties. This is also related to the question of decidable equality. And this is really so normalization is a characterization of open terms. So we want every term in any context to have a normal form so that we can, for example, compare normal forms for equality. And this gives us a way of deciding equality between arbitrary terms. And so this is what this talk is about. So our main contribution is a formalized Agda proof of normalization for a type theory with first-class levels, inspired by Agda itself. So our formalization builds upon the graded type theory project, which is available on GitHub. This started as the basis for some work by Abo, Oman, and Vezosi on decidability of equality. It has since been extended by many other people. So the formalization defines a version of Martin-Löf type theory with sigma types, pi types, an empty type, a unit type, natural numbers, some other stuff that's not in the paper. And our addition is a countable hierarchy of universes and a type of levels, such that the universes are indexed by the levels. And we use extrinsically typed syntax because that seems to be sort of the more convenient approach at the moment to avoid having to deal with transports. So we define an inductive recursive logical relation for open terms and prove a fundamental lemma. If you're a type theorist, this should sound familiar. If you're a category theorist, here's a translation. So we define an inductive recursive model in 3 sheaves over weakenings, and then a normalization model from that by gluing along the restricted Uneder embedding. If you're not a category theorist, just ignore that. And then from that fundamental lemma, we derive a whole bunch of consequences, so injectivity and non-confusion of typeformers, a strong form of canonicity that holds not just in empty context, but in any context that only consists of level variables and type variables. So anything that only depends on levels and types is canonical. And this includes the empty type, so we get consistency as well. And we also get weak head normalization, decidable equality, decidable type checking using a bidirectional algorithm, and full normalization, roughly in that order. So this is sort of based on the same approach as the work by Abo and others. And also soundness of extraction. We show that we can basically compile the type theory to an untyped lambda calculus in a way that preserves the reduction and that also has some form of canonicity. So the syntax for levels is exactly the same as in Agda. So we have a type of levels, we have a 0 level as the sort of bottom universe. We have a successor operation and a least upper bound operation. And we add some judgmental equalities that make level with this structure into a bounded joint similatist. So this just means that the least upper bound is associative, unital with respect to 0, commutative and idempotent. And we also ask for the successor to be an inflationary endomorphism, which is a fancy way of saying that L is less than L plus. which in turn just means that we have this equality. And so the sort of intended model for the type of levels is the natural numbers, but it's not the only model because we don't have an eliminator. But we sort of think of them as natural numbers anyway. And also some reduction rules for the least upper bound that sort of pretend that it's defined by recursion. This is just so that we get some kind of canonicity for levels in empty context. We don't sort of fully normalize levels using reduction because we want it to be stable under substitution. So the sort of full normalization is done later as part of deciding equality. The syntax for universes is also similar to Agda. So if L is a level, we get a universe UL that lives in the next universe, UL+. Each of the universes is closed under pi types, sigma types. We can optionally have the type of levels in the first universe. This doesn't really change anything. So for example, we can form this type of the identity function. So this type doesn't live in any universe because it's sort of too big. So the universe of what's after the quantification depends on the level. So this doesn't live in a universe. So compared to Agda, we don't have a universe omega. So in Agda, this would live in set omega or type omega. We don't have that just for simplicity, but it should be straightforward to add. We also don't have heterogeneous type formers. So in Agda, if you take a product, for example, of two types that live in different universes, you get something that lives in the least upper bound of the two universes. Instead, in our case, you get something that doesn't live in a universe. But we do have some way of lifting types from a smaller universe to a larger one. So we could lift both U0 and U1 to U2, and then the product would live in U2. Okay, so the logical relation is sort of well, the structure of it is sort of standard. So we define reducibility judgments, which are meant to model the typing rules. So this J stands for like either A is a type or T is a term of A, or one of the equalities between types or between terms. So these judgments are defined by well-founded induction on this level L, which is an external level. So it's an ordinal in omega plus 1. And then at a given level, the four judgments are defined by induction recursion. So the judgment for types is defined inductively as an inductive type. And the judgment for terms and the other judgments are defined recursively on a witness that the type is reducible. So for example, in the case of pi types, the reducibility judgment for a dependent function is of that form. So it says that for any extension of the context and any term in the extension, any reducible term of the domain in the extended context, the application is also reducible. So this is sort of standard. Our main addition is in the case of universes. So in order to say what it means for UK to be a reducible type at some external level L, we have to somehow relate the internal levels and the external ones. And we do this using this realizer function. So we say that UK is reducible if K is a reducible level and the realizer of K is less than L. And then given this, we say that a type A, a term A is reducible in the type UK if, roughly speaking, A is a reducible type at the level the realizer of K. So the only surprising thing is maybe the way that this function is defined. So it's defined by recursion on the sort of weakness of reducibility for the level. So the cases for the operations are sort of obvious. We just map them to the corresponding operations on natural numbers. But the case for neutrals is sort of interesting. So in the case of neutrals, we can basically leave the definition or leave the function undefined. So one way to think about this is you can define the realizer of a neutral level as a meta-neutral, so a variable in the meta theory. In the formalization, we use an abstract block, so it's a definition that Agda isn't allowed to use in any way. Another way to think about it is you could define this function as a relation instead. So if you define the graph of the function inductively, then you would just have not have a case for neutrals, and this works out. So so to conclude, we show that type theory with first-class levels, inspired by Agda, is normalizing. We gave a formal proof in Agda using induction recursion to model the universe hierarchy. So some possible future work would be to extend the external hierarchy of universes beyond omega, like in Agda. So I think this should be straightforward. A question that's a bit less clear to me is whether bounded level polymorphism, as in the work of Chan and Weyrich, is normalizing. So this is a bit less clear because if you have bounded level polymorphism, this means that for any level you have a type of levels less than that level. And so if you're in an inconsistent context, then all of these types are inhabited. So given a level, you can always find a level that's smaller than it. And so in inconsistent context, you sort of have an infinite decreasing hierarchy of universes. So I mentioned that paper on non-well-founded universe hierarchies. I'm not sure if it's possible to connect that. So non-well-founded hierarchies in the meta theory and sort of non-well-founded hierarchies in the object theory. So this is something to think about if you're interested. And that concludes my talk. Thank you.
We have questions in the room. In your, if you go back a couple slides, when you had the up K, so you are not defining this on neutrals, but when you have a definition that is using like recursor or some kind of recursion in order to define an element of type level, like where does the reduction actually happen?
So, so this up arrow function takes an element of this type, so a witness that K is reducible and produces a natural number. And the way that it's actually implemented in the formalization is that in the case where K is a neutral, we sort of there's a separate definition for that case, which is 0, but that doesn't matter, and the definition is marked abstract. So Agda never unfolds that definition. So basically, all that matters is that is the other cases. So if you have a neutral and you take the realizer of K plus, you will get 1 plus the realizer of K. but the actual value of the realizer of K doesn't matter in any way.
Well, I'm asking about when you have an expression that does reduce to like 3 or something, but it is an expression that needs to be reduced before it will expose the 3.
Okay, got it. So yeah, so in that case, this is covered by the definition of reducible levels. So this includes, so we sort of say that a level is reducible if it reduces to something that's in one of the forms that we have here. So either it reduces to 0 or it reduces to the successor of a reducible level, or a least upper bound of something that is stuck, or a neutral.
Thanks.
Hi, thanks for the talk. When you have bounded universe level quantification, it's relatively easy to get some sort of conservativity result. You just kind of inline all of your definitions, making like 1,000 millions copy each one for each use, and then you can kind of go back to the naive system with just natural number levels. And do you think there would be any analog of that here, or are you really in a different territory that just doesn't compile down to like good old Martinov type theory with its nice simple hierarchy?
Right. So, the paper I mentioned by Favier and others does something like that. I don't think this is possible with internal levels. I think it's a different kind of beast, basically, because you can have levels in the context. So you can't sort of syntactically say, well, this proof uses n levels, so let's just replace them with natural numbers. So I don't know. Maybe there's a way to do it. I don't know.
Do you have any idea of whether there are reasonable models of that, I don't know, in set theory or in other things, or is this just kind of a syntactically reasonable, but like we have no clue what it might denote?
So I think, Ondřej's paper builds a sort of general class of models for internal levels, and I think it's general enough in the sense that, for example, the set model models first-class levels. So, I mean, it would be interesting to investigate, like, which models exactly can support first-class levels, or what this even means. But I think, I don't think the models of this are too exotic. Like, they should be fairly reasonable things.
Okay, thank you.
One last question.
Brilliant talk. Thank you very much. Could you perhaps, suppose someone was starting a new proof assistant project, would you be able to provide a brief comparison between your approach and, say, universes via Tarski, and like the pros and cons, like which one you would go for? Thank you.
So I think the difference between Russell and Tarski universes basically doesn't matter here. So this would be another thing to investigate, but I think the fact that we use Russell universes is sort of just a way to align with the way that type theory is presented syntactically. But I don't think there's any difference sort of semantically. But maybe for a proof assistant, Russell universes are more sort of usable or intuitive. But I mean, there are also other approaches to universes. So.
Thank you. Let's thank our speaker.